So now we will also look at, in fact I will not get into the proof of this, I will leave some of it as exercise, but we will look at one more reduction that I said at the beginning. So if you recall, at the beginning of this topic we looked at 3 problems, we looked at division, we looked at powering, and we looked at iterated product. So we saw that division and powering are NC1 equivalent, right. So division reduces to powering and powering reduces to division, and what we have seen here is that powering reduces to computing iterated product. Well, powering reduces to iterated product is actually easy. So we have seen that. So the next result that we will see is that iterated product NC1 reduces to powering, right. So actually these 3 problems are NC1 equivalent, all 3 of them, and this is actually not very difficult, I mean some 2-3 small ingredients. So what is the iterated product problem? So we want to compute product of these xi's. So what we will do is we will set let x be equal to the number 2 to the power 2n plus 1, okay. So given n I can of course compute this, given n I can get 2n, and 2 to the power 2n is just adding 2n many zeros. Next, use powering to compute the number 2 to the power I think x square, right. What do I need here? We will compute x raised to 2n. So let us call this as y, and now what we will show is that, so this y that we have, okay. So if we look at the following bits of y, okay. So the bits of y from position 2n square to 2n square plus 2n minus 1, okay, is exactly equal to the binomial, well, it is equal to 2n choose n, okay. So essentially what I am saying is that if you look at y, okay, so let us say I look at this y, okay, so I have my bits of y, so let us say it is some y t minus 1 up to y 0 I have. Now look at the position y of 2n square up to y 2n square plus 2n minus 1. So this term is exactly equal to 2n choose n, okay. Now why we have 2n choose n, I will just come to a moment, but just let us first observe that we can get y, okay. So if I can actually do powering, I can compute x raised to the power 2n and I can get y, and I can of course select these many terms from y. Now, why is this important? What is special about 2n choose n? So, 2n choose n is actually a good modular sequence. Okay. So, I will just leave the remaining as an exercise. So, what you can see is that show that Mn equal to 2n choose n is a good modular sequence. And what we have seen just earlier is that if somebody gives me a good modular sequence, I can compute iterated product. Okay. So, 4 is using the value of 2n choose n, get iterated product as earlier. Okay. So, the only part that remains is to prove this is this is a good modular sequence, and that you can figure out, right. So, basically there are 3 things that you have to show. You have to show that Mn is greater than 2 to the power n, it is less than or equal to 2 to the power n to the power d for some d. So, you have to come up with a d, and you have to show that the only factors of Mn are the only prime powers that divide Mn are bounded by a polynomial. Okay. So, that is it. So, any questions? Okay. So, let us move. Which one? So, how many bits will this have? Okay. So, if you look at x, x has 2n many bits, correct. So, x has 2n many bits. So, if I have 2n bits, raised to the power log n will give me how many bits? So, it will be some 2n into log n many bits, right. So, I have that many bits in y, 2n into log n, because I mean n has log n many bits, right. Okay. So, it is to 2n, right. So, it will be 2n into 2n, yeah. So, y will have actually about n square many bits, 2 to the power 4n square many bits. So, there I am looking at the bits from position 2n square up to position 2n square plus 2n minus 1 in that string. Mm-hmm. 2n square, right. Oh, yeah. This would be 2n square to 2n square plus 2n, correct. Yeah. I do not even have that many positions. Yeah, here it is correctly written, here it was incorrect. Okay. Anything else? Okay, so let us move to something else now. So, we have seen these classes, right. So, we have seen these classes NC. Okay, so let me just write what I want to discuss next. So, we will look at the relation between bounded depth circuit classes and other uniform complexity classes. Okay. So, we have seen these classes NCI, ACI and so on, and we have also seen the following results. So, we have seen that, well, NCI is of course contained in NC I plus 1, ACI is contained in ACI plus 1, NCI is contained in ACI, and ACI is contained in NC I plus 1. Okay. So, the first three are actually definition, it follows directly from definition. The fourth one just follows, I can take every gate of unbounded fan-in and I can replace it with a log depth circuit of bounded fan-in. Okay. So, that gives me the fourth one. Now, what are the relationships, I mean what relation do we know between these classes and other uniform classes? By uniform classes I mean classes such as P, maybe NP, or maybe some smaller classes. Okay. So, let me define these space bounded classes. So, again if you have had some exposure to complexity, you would know these classes, but for the sake of completeness I will just define them. So, L is the class of decidable by a deterministic Turing machine in log space. Similarly, we have NL, which is a class of languages decidable by a non-deterministic Turing running in log space. Okay. And some of the known results that we have in this area are that, well, L is contained in NL, NL is contained in P, of course P is in NP. Okay. And one more result that we will be using, again this is a well known result, that directed graph reachability is complete for the class NL. Okay. So, as I said that these are some of the results which are taught in any basic complexity course or even in a theory of computation course, and I am going to assume that you are familiar with these results, but even if not, I mean you can just take them as granted and we can move on. This is something that can easily be looked up. Okay. So, what we will prove is the following, that where does these classes sit with respect to these classes. Okay. So, what is the relation between these bounded depth classes with respect to these uniform complexity classes? So, what, so I will come to that. Okay.